phenomenon that is so remarkable challenges not just our understanding of physics but also the basic structure of reality itself, which exists in the exquisite tapestry of the quantum universe. This chapter sets out on an intriguing voyage into the mysterious world of quantum entanglement, a phenomenon that defies conventional comprehension. Imagine the tiniest particles that make up our universe's structure entwining in a way that violates the laws of conventional physics. Despite the enormous cosmic distances separating them, this entanglement, as it is correctly dubbed, seems to be a mystifying relationship where the condition of one particle instantly influences the state of another. It seems as though these particles communicate instantly and defy the limitations of time and space as we understand them. Our classical physics-based intuition struggles to understand the complexities of this occurrence in the real world. Once correlated, entangled particles maintain a connection so strong that one particle's state becomes inextricably tied to the state of its entangled partner. The very underpinnings of our comprehension of cause and effect are put to the test by this connection, which endures even when these particles are separated by distances of many light years. Beyond the realm of theoretical physics, quantum entanglement has far-reaching effects. Its fundamental issues regarding the nature of reality have intrigued both scientists and philosophers. Does this phenomenon imply the presence of unfathomable worlds or secret dimensions? Or does it suggest a more fundamental unity of the cosmos, one in which everything is tightly interconnected in ways we are only now beginning to understand? We encounter both mind-boggling paradoxes and the breathtaking beauty of the universe's deepest mysteries as we dig deeper into the mysterious world of quantum entanglement. Buckle in for the ride ahead, which is sure to alter our perspectives, broaden our horizons, and reveal cosmic mysteries in ways we never imagined. We begin our journey into the mysterious world of quantum entanglement by delving deeply into the underlying ideas that underlie this perplexing occurrence. In this fascinating voyage, we will reveal the complicated dance by which pairs or clusters of particles entangle one another, creating a puzzling and meaningful bond. It is a situation in which the fundamental laws of classical physics are suspended and the quantum world assumes primary significance. When particles are entangled, they reach a level of interconnection that defies the limitations of conventional knowledge. No matter how far apart they are from one another, whether it's just a few nanometers or the enormous cosmic voids that encompass the entire universe, their attributes interact in a way that defies logic. Previously thought to be distinct and autonomous, parameters like spin, location, or polarization start to intertwine and act as though they are connected by a thin, ethereal thread. Even though it is puzzling, this phenomenon provides a tantalizing insight into the deep mysteries of the quantum realm. It entices us to explore its depths further in order to unravel the riddles of entanglement and, in doing so, gain a better understanding of the very nature of reality itself. The EPR paradox was a quantum entanglement demonstration experiment that was first proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. This groundbreaking thought experiment posed a serious challenge to the fundamental assumptions of quantum theory and served as a potent illustration of the unsettling connection present in entangled particles. The three physicists saw the EPR paradox as a situation in which two particles that were produced from the same source and subsequently separated would be entangled in such a way that their properties would instantly correspond, regardless of the physical distance that separated them. The idea that information may ostensibly travel faster than the speed of light seems to challenge traditional ideas of causality and locality and is fundamentally incompatible with Einstein's theory of special relativity. The dilemma exposed the puzzling properties of quantum entanglement, whereby entangled particles appear to have a secret link that defies conventional understanding. The Bell inequalities were eventually developed as a result of this challenge to the validity of quantum theory, which also confirmed that quantum entanglement is a genuine and essential feature of the quantum universe. The EPR paradox remains a pillar in the investigation of quantum mechanics and the profound philosophical issues it brings up regarding the nature of reality itself. Bell's theorem and revolutionary tests that verify quantum entanglement. Bell's theorem, a cornerstone of quantum mechanics, proves the existence of quantum entanglement and the strong connections it causes between entangled particles, upending classical physics. John Bell, a physicist, developed this theorem in 1964, and it has since been put to the test in groundbreaking experiments, demonstrating the enigmatic and non-classical nature of quantum entanglement. The Bell theorem. Bell's theorem is based on the concept of hidden variables, which postulates that particles' behavior is determined by underlying, unobservable features, making it predictable in terms of classical physics. The Bell's inequality, however, was a testable inequality that was proposed by the Bell's theorem to enable tests to discern between classical physics predictions and quantum mechanics predictions. The investigations. 1. Aspect's experiment, 1982. Alan Aspect and his team carried out one of the first experiments to prove Bell's theorem in 1982. They took advantage of entangled photon pairs that were emitted from calcium atoms. These photons were delivered to two different detectors, each of which had a polarizer in front of it that could be adjusted in orientation. Strong evidence against the existence of hidden variables and in support of quantum entanglement was provided by Aspect's experiment, which demonstrated that the correlations between the measurement results of the entangled photons violated Bell's inequality. 2. Clauser-Horn-Shimony-Holt experiment, CHSH, 1969. An essential further test of Bell's theorem is the CHSH experiment. It involved utilizing different polarizer orientations to measure correlations between entangled particle pairs, such as electrons. Bell's inequality was also broken by the findings of this experiment, which Clauser, Horn, Shimony, and Holt carried out in 1969. This demonstrated that traditional physics could not account for the observed relationships between entangled particles. 3. Friedman and Clauser experiment, 1972. John F. Clauser and Michael A. Horn carried out an experiment in 1972 that provided additional evidence of Bell's inequality being broken. They evaluated the correlations between their measurements taken at various angles using entangled photons. The outcomes confirmed the predictions of quantum mechanics and the concept of quantum entanglement once more. Implications. Our understanding of the quantum world has been profoundly affected by these groundbreaking investigations. The reality of quantum entanglement, in which particles can connect in ways that defy conventional explanations, was proven. The breach of Bell's inequality calls into question the conventional idea of hidden variables that might influence a particle's outcome and strongly argues that quantum mechanics provides a more accurate account of particle behavior at the quantum level. To sum up, Bell's theorem and the tests that put it to the test were crucial in revealing how fascinating and counterintuitive quantum entanglement is. They have demonstrated correlations between entangled particles that cannot be accounted for by classical physics, which has altered our perception of the underlying ideas guiding the quantum world. The concept of quantum entanglement, sometimes known as spooky action at a distance, goes right to the core of how we perceive the world. It contradicts conventional wisdom and poses significant problems for our understanding of the universe's structure. In this investigation, we'll set out on a quest to understand the mysterious nature of quantum entanglement, which gives the measurement of one entangled particle the ability to instantly ascertain the condition of its distant companion. This amazing connection continues, seemingly defying the celestial speed cap imposed by the constant speed of light. In addition, we will investigate the fascinating phenomenon known as quantum teleportation. Thanks to the occurrence of entanglement, this amazing concept enables the transmission of the quantum state of one particle to another, even across great distances. The future of technology and research will have access to previously unimaginable options as a result of this quantum mechanics discovery, which has the potential to change industries like secure communication and quantum computing. The mystery of quantum entanglement reaches far into both the theoretical and the practical, luring us to investigate the very foundations of existence. As predicted by quantum theory, this enigmatic occurrence has significant ramifications that repeatedly call into question the tenets of our comprehension of the cosmos. Philosophically speaking, quantum entanglement challenges us to consider the idea that particles, once entangled, become intrinsically connected, despite the enormous distances separating them. With its suggestion that the fundamental components of the cosmos are intertwined in ways that go against conventional intuitions, this idea raises important issues regarding the nature of reality. It challenges us to reevaluate how we perceive causality and the structure of space and time. Were we able to catch a glimpse of a more profound connectivity that goes beyond what we normally believe to be the physical world? In the real world, quantum entanglement presents the prospect of radically new technological developments. Quantum technologies, including quantum computing and quantum communication, have taken advantage of the phenomenon. In areas like encryption, drug development, and materials science, quantum computers have the ability to tackle complicated problems faster than traditional computers. Entanglement-based quantum communication promises unmatched levels of data security because any attempt to eavesdrop would cause the entangled particles to break apart, immediately alerting the parties involved. Furthermore, quantum entanglement suggests the existence of instantaneous, spooky action at a distance, challenging the limitations of classical information transfer. This possibility has significant ramifications for how we see the universe's constraints on information flow. In sum, quantum entanglement invites us to embark on a philosophical journey to reconsider our core conception of reality while simultaneously providing us with realistic opportunities to use quantum technologies to change our environment. We stand on the threshold of a new age in science and technology that has the potential to transform the fundamental underpinnings of our existence as we continue to delve deeper into the secrets of entanglement.